All right, we're going to go through all 12 problems on here. Some of them I'm just going to give you the energy setup so you can track the energy. Some of them we'll do in complete detail. So starting with number 1, we've got a base runner starting out at 3.6 meters per second. Looks like there's friction acting on it, and after friction's done, the speed goes to 0. So the energy transformation here is starting out with kinetic based on this initial speed of 3.6, having some negative work from friction, and ending with no kinetic, no height, no spring, so nothing. So this would be 1/2 mvi squared minus the force of friction times distance. So mu mg times distance on a flat surface gets you to 0. Then you should be able to plug in and solve for distance. That will get into your question for B. The answer to A would just be however much kinetic you started with, because friction is going to get rid of it to get you to your total of 0. Number 2, we have a bullet that is speeding up in the A barrel. It says it starts from rest, so we're going to have no height change involved here, no kinetic at the beginning, so starting out with 0, plus some work from the expanding gas as well as in the barrel, gets you to the kinetic at the end, and we know there's kinetic at the end because there's a speed at the end. So we would have force times distance for work, and 1/2 mvf squared for final kinetic. So we would have force, which is unknown, the 41 centimeters or 0.41 meters, half 2 grams, which is 0.002 kilograms, times that final speed of 335 squared, and we could solve for force. Number 3, we have a car that is going down a highway, 2 forces acting on it. Looks like it starts at rest again, so no kinetic, no height change involved here, so no potential either. We've got plus work done from the first force, which is that 1010 Newton force, minus work from that 960 Newton force should give us our final kinetic. All right, so plus force times distance minus force times distance equals 1/2 mv squared. 1010 times the 35 minus 960 times the 35 should equal 1/2 times the mass, 2150, times Vf squared. If you want to subtract these forces first and just call it a 50 Newton net force, that would work as well. Number 4, we have something starting out at 2 meters per second, so we're going to have some initial kinetic. We have an initial speed. We have some negative work from friction that's going to slow us down, and it says we're going to stop, so we're going to have 0 at the end. So again, initial energy minus the work along the way gets us to our final. 1/2 mv squared, which would be the 2 here, minus, again, mu mg times distance. That's a force of friction times distance, would get us to our final energy of 0. Notice here we're not tracking the person kicking the puck to bring it up to 2 meters per second. What we're concerned with is starting at 2 and friction slowing it down until it stops again, which is why we make our 2 the beginning over here and 0 for our final energy. 5, we involve an incline. All right, so we have an initial speed, so it looks like we're going to have some initial kinetic. We're starting at the bottom of the incline, so no height at the beginning. So no potential there, but we do have some kinetic at the beginning. Along the way, we've got an applied force of 100 newtons, and that's parallel to the ramp. And then we have some negative work happening from friction, also parallel to the ramp, just opposite. And then we are looking for its final speed, so we're going to have some final kinetic, and at the end we've gained some height, so at the end we're going to have kinetic and gravitational. We also might have to do a little bit of trig here. We know the distance on the ramp is 5.1, 20-degree incline, so we can find the height over on the side just by doing 5.1 sine of 20. So the height looks like 1.74. So setting this up, 1/2 mv squared plus the applied force times the distance minus the friction force times the distance equals 1/2 mvf squared. That's where our final speed's going to be, plus mgh. So 1/2 mvi squared plus applied force times distance And then minus mu mg cosine times distance for friction force on a ramp equals half mvf squared plus mgh. And again, rather a complicated equation here, but if we track the energy, we can kind of see where every piece came from. This is our initial energy part. Here's what happened along the way with the two different forces that are doing work. And here's our end position at the top of the ramp where we are moving and we have some height. Right, so we should have numbers everywhere here. Our initial speed was 1.5, so that would be VI. Our applied force is that 100 newtons. We don't need a cosine there because it's pushed parallel to the ramp. We know mu mg cosine of 20. And the distance for both of these is that 50 or 5.1 meters. 1 half mvf squared, there's where our final speed's going to be. And then mgh, this 1.74 will go in for h. Number 6, we've got somebody starting out at the bottom of the ramp with a speed of 38 meters per second. No height at the bottom of the ramp, so no potential there, but we do have a lot of initial kinetic. No work because we only have conservative forces. The only force acting on this guy as he goes up to his max height is gravity. So we don't have any work in between, completely conserving our total energy. At the end, we're still moving, so we have some kinetic final. We're just slower. So since our kinetic went down because our speed went down, it had to go somewhere, and it goes into the gravitational potential that we have at the end because we've gained some height. So half mvi squared equals half mvf squared plus mgh. Our mass would cancel out, so it doesn't matter that we don't know it. This initial speed's 38, this final speed's 36.4, and that would let us solve for the height. Number 7. Right, we just have again, a simple height change and speed change problem involved. We don't have any friction, so no non-conservative forces or anything like that. So for finding the speed of it at B, we're starting at rest at A, so we're just going to compare energy at A to energy at B, and we know, again, they have to be the same since there's no friction. At A, it starts at rest, so there's just gravitational potential. At B, there's no height anymore, but it gains speed. So all of that gravitational we started with turned into kinetic. So just an mgh equals half mv squared comparison. We can do the same thing for C. We can either compare A to C and go all gravitational at A equals a mix of final kinetic and final gravitational at C using C's height. So the height here would be 5 meters, the height here would be 2 meters, and this kinetic would make up the difference in the potential energies. Or, since the energy is the same everywhere, if you wanted to compare B to C, that would also work. At B, it's all kinetic. That would become the initial. At C, again, you have final kinetic and gravitational. Right, so again, energy is the same everywhere. Any comparison of 2 points, one that you're interested in, one where you know what's going on, will work out for you in 7. Number 8. Again, another incline. This time it's frictionless. The child's going uphill and starting with a speed of, the child's going downhill, ending with a speed of 2.1 meters per second. We want to know the height. So if we draw this out, this is what we want to know, the height here. So we're going to compare the top to the bottom of the incline. At the top, we start out with all gravitational. At the end, we've converted that all to kinetic. Same total because there's no friction acting along the way to take any energy out. No applied forces to put any energy in. So mgh at the top is going to be half mv squared at the bottom. 2.1 would go here. Mass would cancel even though we know it. But we can go ahead and solve for this height. Number 9, where things start to get a little bit more complicated. We're starting out 10 meters above the ground. And the copper ball is going to hit the ground, and then it's going to go 2.6 millimeters more. Not that that's a huge deal, but technically our total height change is 10 meters plus this 2.6 millimeters, or our total height change is 10.0026 meters. And if you just use 10, you probably get really close to the answer. It's not going to make that much of a difference, but technically it's there. At the very beginning, since we're just dropping this, we're starting out with just gravitational potential at the top. And at the end, we've hit the ground, so we gained kinetic along the way, but whatever kinetic we had when we hit the ground got lost by the amount of work being done by the plate when it hit. So technically, our final is actually 0 because we have no height anymore and we don't have any speed anymore if we track it all the way till it is done leaving this dent. So where did the energy go? It was negative work taken out by the applied force from the floor. Right, so yes, technically there was a transfer of gravitational to kinetic right before it hit, but then that kinetic got lost from the work done from the floor. So I'm going to go mgh for my gravitational, and then minus force times distance for the amount of work done. If you wanted to break it up and say gravitational to kinetic, find the impact speed, and then go kinetic minus the work done, you could do it as a two-part problem, but I'm going to do it all together. mgh, I know my mass is 5.55 kilograms, g is 9.8, height is 10.0026, minus the force that I'm interested in solving for, and then the distance. Well, where did work get done by the floor? Not over the entire 10 meter 0.0026 distance. The work only got done in this last little portion in contact with the floor. So the distance is only this 0.0026, the distance it was in contact with the floor. And again, that would get rid of all my energy, bringing me to a final total of 0. When this would let me solve for my force, which I get that 2.09 times 10 to the 5th newtons, or 209,000 newtons. Number 10, Tarzan on the swing. This is going to be another geometry problem where we have to have our radius or our length of our swing. Maybe we could call that an L for length of our of Tarzan's vine as it swings from the side to the bottom. But this length is the same whether he's over here or over there. He did change height, and the height change is the difference between the two positions. So if we make a triangle here, and we have that 30-degree angle it gives us up there, then this distance is our cosine, so that makes the missing part r, which is this whole thing, minus this r cosine to give us our leftover down here. So that's the first thing. I've got to find out my height change, r minus r cosine, so the length is 33 minus 33 cosine 30. And that's 4.42 for my height. That's a much easier problem now. It says Tarzan lost 4.42 meters in height. How fast is he going at the bottom? That's a much easier problem to solve. So we can just go gravitational at the top to kinetic at the end, mgh, to half mvf squared, and take our 4.42 and plug it in for height there, solve for our final speed. In part B, Tarzan's going to have some speed at the beginning too, so we'd have to add in some kinetic initial, plus that same gravitational will get us our kinetic final. That would mean there's more total energy, the same gravitational plus some extra kinetic, so it makes sense that we'd have more energy at the end as kinetic, which is why we get to go faster at the end and get a higher answer for 10B. Number 11, just a height change again. We never make it to the ground here, so we've got two choices. We could use the heights that it gives us, the 5.2, the 3.2, and the 2 meters, in which case we would need to have potential energy everywhere based on these heights. So even comparing A to B or A to C, it looks like we're released from point A, so at least it's all potential up there, but when we make it to B or C, we'd have some kinetic and some gravitational. Or what we could do is just call C the lowest point 0 and say B is 1.2 meters higher than C and A is 3 meters higher than C and go with those heights, which means we would not need any potential there. Just a different way of measuring the height. Either way, we would have gravitational potential at the beginning, gaining some kinetic at B, and some gravitational there. Again, it's just a question of where you're measuring your height, from the ground or from part C. Right? As long as you're consistent, it doesn't matter. Right? Same deal with comparing to C. Right? We've just converted a little bit more of our gravitational potential into kinetic energy. Last one, number 12. We've got a diver stepping off of an 11-meter tower, dropping straight to the water, and then he goes 5 meters below the surface. So this is another one where we could do it as two parts if we want to. We've got our swimming pool that goes 5 meters down, and our diving board that's 11 meters tall. What I'm going to do is choose, again, to do it all together. There's a total height change of 16 meters. So I'm going to go gravitational potential at the top, minus some work done by the water, brings me to rest at the bottom, where I have no energy. No height, no speed, no energy. So I'd have mgh minus force times distance equals my no energy at the bottom of the pool. My height here would need to be 16, right? That's my total height change, 16 meters. But the pool doesn't do work over the entire 16 meters. The water doesn't do any work when I'm in the air. The water only does work over these last 5 meters. So this distance would be 5 here. So the mass 82, g 9.8, height of 16 minus force times 5 equals 0. That would get me my force. Couple other options for this one. I could call the 0 water level. I could give them a height of 11 at the beginning and some negative potential of based on a height of -5 at the end. That would also work. Or if I wanted, I could break this into a 2-part problem. Just look at the diving board to the water part, go gravitational to kinetic based on a height of 11 meters, find the speed right here, and then do another problem of kinetic and potential based on a height of 5 meters minus some work, brings me to the bottom. But I think it's easier to kind of combine everything together. At the very beginning, height and no initial speed. Yes, some kinetic was gained in the middle, but we don't care. At the very end, we lost our height, we lost our speed, so we end with 0. And again, some negative work was done in the pool along the way.